Hello everyone, welcome back. In this video, we're going to look at some of the properties of the definite integral that will help us evaluate certain integrals. Now, the first property states that we can swap the limits of integration by introducing a negative sign. So the integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. Now, the second property states that the area under the curve at a single point is equal to 0. So we look at some function y equals f of x, and if we want to integrate from a to a, then this represents the area underneath the curve at the point where x equals a. And we know that the area of a line is equal to 0 since it has no width. Now, the third property states that constants can be pulled outside of the integral. So the integral from a to b of c times f of x is equal to c times the integral, where c is any constant. The fourth and the fifth properties states that the integral of the sum or difference of two functions is the sum or difference of their integrals. So the integral of f plus g is the integral of f plus the integral of g. And the same thing will hold for the difference of the two functions. Now, the last property states that we can separate the integral from a to b as the integral from a to c plus the integral from c to b. So let's have a look at an illustration of this property. So suppose this is our function, and we're integrating from a to b. So the integral from a to b is equal to the integral from a to c plus the integral from c to b. So now let's have a look at some examples of using these properties to evaluate certain types of integrals. So let's have a look at the integral from 0 to 1 of the square root of 2x plus 1 plus the root of 3x plus 1 dx. So here we're dealing with two different functions. So we use one of the properties. We can separate the integral into two separate integrals. This is the integral from 0 to 1 of the root of 2x plus 1 dx plus the integral from 0 to 1 of the root of 3x plus 1 dx. So now we can evaluate each integral separately, and we will use a u substitution. So in the left integral, if we let u be 2x plus 1, then du is going to be equal to 2. So then du over 2 is equal to 2x. Now over on the right, we'll make another substitution, and we'll call this v. We'll let it be 3x plus 1. Then dv over dx is equal to 3. So then dv over 3 is equal to dx. I'm using a different variable to not get confused with the other substitution. So now our integral becomes the integral from x equals 0 to x equals 1 of u to the 1/2 times du over 2 plus the integral from x equals 0 to x equals 1 of v to the 1/2 times dv over 3. Then we'll use the property that we can move constants outside of our integrals. So we have 1/2, the integral from x equals 0 to x equals 1, u to the 1/2 du, plus 1/3 times the integral from x equals 0 to x equals 1, v to the 1/2 dv. So now we can integrate. We have 1/2 times u to the 3/2 over 3/2, and we evaluate at x equals 1 and x equals 0, plus 1/3 times v to the 3/2 divided by 3/2, and we evaluate this at x equals 1 and x equals 0. So now let's simplify. We have 1/3. We can substitute back our original variable. So u was 2x plus 1, and this is raised to the 3/2, and we evaluate this at 1 and 0, and we add this to 2/9, and we substitute back the original variable, which is 3x plus 1, raised to the 3/2, evaluated at 1 and 0. So now we substitute the upper and lower limits. So we have 1/3 times 2 times 1 plus 1 to the 3/2. And we subtract the evaluation at 0. So it's 1/3 times 2 times 0 plus 1 to the 3/2. And we add this to 2/9 times 3 times 1 plus 1 raised to the 3/2 minus 2/9 times 3 times 0 plus 1 to the 3/2. So simplifying, we get 1/3 times 3 to the 3/2 minus 1/3 times 1 to the 3/2. And we add this to 2/9 times 4 to the 3/2 minus 2/9 times 1 to the 3/2. So now this becomes 1/3 times the square root of 27 minus 1/3, and we add this to 2 over 9 times the square root of 4, which is 2, and 2 cubed, which gives us 8, minus 2/9. So here we can make a common denominator of 9. So that gives us 3 root 27 minus 3 plus 16 minus 2, and this is all over 9. And simplifying, we get 3 root 27 plus 11 all over 9. In the next example, we have the integral from pi to pi times sine squared of x cos to the 4th x dx. So if we look at the limits of integration, we're integrating over the same value. And so we know by the second property that this integral is equal to 0. Now in the next example, we have the integral from 0 to 1 of the absolute value of 2x minus 1 dx. So since we're dealing with the absolute value function, let's rewrite it so that we have a piecewise defined function. Recall that the absolute value of x is x when x is greater or equal to 0, and it's negative x if x is less than 0. So the absolute value of 2x minus 1 is going to be 2x minus 1 whenever 2x minus 1 is greater or equal to 0, and it's the negative of 2x minus 1 whenever 2x minus 1 is less than 0. So now let's rewrite it so that we can read our domain more easily. So we solve for x in the inequality. We get that the absolute value of 2x minus 1 is 2x minus 1 when x is greater than or equal to 1/2, and it's the negative of 2x minus 1 whenever x is less than 1/2. So notice that the absolute value of 2x minus 1 will be a different function if we're working with x greater than or equal to 1/2, or when we're working with x being less than 1/2. And since we're integrating between 0 and 1, we need to split the integral into two separate integrals. So if we use the 6 property, we can write this as the integral from 0 to 1/2 plus the integral from 1/2 to 1. Now when x is between 0 and 1/2, we know that the absolute value of 2x minus 1 is going to be negative 2x minus 1. And when x is between 1/2 and 1, we know that the absolute value of x is going to be 2x minus 1. So now let's write this as the integral from 0 to 1/2 of negative 2x plus 1 and now we can find the definite integral by integration. So if we use the fundamental theorem of calculus, we need to find the antiderivative of negative 2x, which is negative 2 times x squared over 2 and the antiderivative of 1 is equal to x. And we evaluate this at 1/2 and 0. And for the second integral, we have the antiderivative of 2x, which is 2 times x squared over 2, minus the antiderivative of 1, which is x. And we evaluate this at 1 and 1/2. And so simplifying, we get negative x squared plus x, evaluated at 1/2 and 0, plus x squared minus x, evaluated at 1 and 1/2. So we have negative of 1/2 squared plus 1/2 minus negative 0 squared plus 0. And we add this to 1 squared minus 1. And we subtract 1/2 squared minus 1/2. So simplifying, we have negative 1/4 plus 1/2 minus 0 plus 0 minus 1/4 minus 1/2. So negative 1/4 plus 1/2 is positive 1/4. And we subtract 1/4 minus 1/2, which is negative 1/4. So that gives us 1/4 plus 1/4, which is equal to 2/4 or 1/2. Now in example 2, what we're given is that the integral from 2 to 8 of f of x dx is equal to 7, and the integral from 2 to 4 of f of x dx is equal to 6. And using this information, we want to determine what the integral from 4 to 8 is under the function f of x. So let's draw a diagram of what we're given. So suppose we have some function and so the integral from 2 to 8 is equal to 7. Okay, so that means the area under the curve on this interval is equal to 7. Now we're also given that the integral from 2 to 4 is equal to 6. Okay, so this region is equal to 6. And what we're after is the integral from 4 to 8. So the area under the curve from 4 to 8. And so what we're after is just the area from 4 to 8. So if we use the sixth property, we know that the integral from 2 to 8 is equal to the integral from 2 to 4 plus the integral from 4 to 8. And so we can solve for the integral from 4 to 8 by subtracting the integral from 2 to 4 from both sides. And so the integral is going to be equal to 7 minus 6, which is equal to 1.